Hello, I am going live because American friend have requested me to make a video in English so that everybody can understand. So to explain this really simple, there is a heat loss inside the engine at all times, and it is a result of a falling electromagnetic field. So by taking out the heat loss from the engine, instead of the heat loss just going internally and making a heat band inside the engine, you can take out the heat loss, or varmetapet. You take out the heat loss, you put it in this box where you have a lot of switches. And this box is very simple. Inside this box is lots of condensators, capacitors, and a lot of wires. So a mess inside there, but it works. So again, I'm online because a friend in the States, United States of America, have requested me to make this video in English, as he doesn't understand Norwegian. So I'm just making a short video in English just to explain a little bit. And when it comes to three-phase engines, all of them, when connected to the house on three-phase house outlet, they use, example, this engine from 1952 will use not less than 600 watts, and that engine there is a 5.5 horsepower engine, will consume almost 800 watts. I had it to run on three-phase. If I don't remember incorrect, it was 798 watts on three-phase outlet from Norwegian in Norway many years ago. This engine here is ABB engine. What is it there? It's 2.5 kilowatt. So, and that there will use easily more than 750 watts from if you connect it to the three-phase house outlet. And this engine here is 0.5 horsepower engine. Will consume a little bit less than those bigger engines, and but on this system, you actually as you see, I have this ring trafo here, okay, and this ring trafo transformed down to if the input is 230 volts, the output will be 110 volts. So what I do here, I actually reduce the volt input, and I also here there is 380 volts configuration, and there is 220 volt configuration. So in E mode you get which it is now, okay, you can see there those three on top there is connected together, which is visible here with those. So these three is connected together, so it is adjusted for 380 volts, and that's very important. So because the engine becomes more efficient when you run it in E mode, okay. So the point is that you have to have as little volt in as possible, and the engine has to be configured for the highest possible voltage. And okay, you know, a volt times amp is watts. Okay, so by reducing the volt input, I can reduce how many watts this engine will use. Okay, you turn on this engine now. Now it runs at 174 volts or so. Amp is 0.6, 0.06, and the watt is 3 watts. So this engine now runs on as little as 3 watts. And the reason for that is that the heat loss that is inside the engine has the ability to come out on the cable that goes into that box there. And that is this speaker cable. And this speaker cable is connected here and there. Okay, so you have one leg on the 3-phase. You have 3 outputs, okay, or inputs, shall I say instead, where these 2 cables here goes in here and in there, where I then emulate the last phase on the engine here between these 2 available legs. It doesn't really matter if I emulate that one and that one, or that one and that one, doesn't really matter. In this case it is between this one and this one. What happens is that the back EMF inside the engine has the ability to escape the engine before the back EMF or the heat loss make a break on the engine. Because, I easily explain it, let's say on this is just a generator, but if the drive pulse starts here, there's 50 drive pulses per second here in Sweden at least. States have 60 Hz. So if you move the disc from here to there, that's one drive impulse. And from there to there is the next one. But before the next one, it has to rotate to there. And from there to there, you have a falling electromagnetic field that will actually try to move the engine the other way. And the reason for that is that the sine wave goes like this, okay? And this is 0 here, this line here is 0. You have the sine wave like this. When the sine wave is on top, then the drive pulse is down. But you have something that happens from here and down to the 0, okay? And from top to 0, you have a falling electromagnetic field. What happens to that field? Yes, well, any electromagnetic field in movement will create an electric current, which again will create an electromagnetic field. So the falling electromagnetic field from top, when the drive pulse is down and to 0 again, will create a brake force. That brake force is the back EMF or the heat loss. Normal science will say that you cannot take out the heat loss from an engine. And of course, normal science doesn't understand that you can, because they just call it heat loss or varmetap in Norwegian language. And because of, they just state it is a loss, of course. And of course it is a loss. But the point being is that loss is approx 40 to 50% depending on the engine. What type of engine it is, what kind of configuration you have connected it, and so forth. So it can be up to 50%, and if you have magnetic engines, permanent magnetic engines, the heat loss energy can become over 50% of the input, which means that the heat loss is breaking the engine with somewhere between 40 to 50% of the actual input energy. In some cases even more. And so you actually waste, by running this engine from the net power in your house, on 3-phase net power from your house, you are actually wasting so incredible much energy just to have this spinning, because the engine has to overcome the heat loss. And that is why a typical engine like this will use 600 watts on the 3-phase outlet from the house easy. And this one 800 watts easy. And that blue one there, not less than 600 watts for sure. It's as I showed just a few minutes ago, it's a 2.5 kilowatt engine, so it will, and it is in poor condition as well, so maybe more than 900 watts, who knows. I never tested that one, on the 3-phase outlet. I did test this one, 798 watts, so I'm just repeating myself a little bit, just to, you know. And anyway, so that is a large amount of energy that just will stay inside the engine and create magnetic friction, lens effect if you want. But instead of doing that, I'm taking out the power on these two legs, and since a condensator, a capacitor, has less friction in taking energy into itself than the engine, because electrons will jump to the easiest route, right? Always the easiest route. And therefore, the back EMF or the heat loss will always jump to this cable here, into the capacitor bank. And when the capacitor bank is correct adjusted, then the engine will be in harmony with itself. And that is the reason why we are running this engine here on 2 or 3 watts, sometimes down in 2 watts. And what we are actually doing here, inside this box there is lots of different sizes on capacitors. And by altering the capacitance value, by switching these switches here, is typically for very large engines, and also start capacitor, start condensator, which you can also hear if I turn on this. Now you hear a difference on the engine. Okay, and also when I turn on the start cap, the watt goes up to 32, 31 watts or so. And even more if I turn on more. Well, so it makes a sound different, and the reason for that is that when you adjust the timing here, because that's what you're doing, because a condensator that is small will empty faster, while a condensator that is big will empty slower. So in fact, when I turn on the start capacitor here, the engine is not in harmony with itself, it's not in resonance